Okay, welcome everyone to the 108th meeting of New Directions in Group Theory and Triangulated Categories. Our speaker today is Jon Woolf from the University of Liverpool, and the title of his talk is Heart Fans as Universal Phase Diagrams.
Okay, thank you, Rudy, and yeah, thanks for the invitation and the opportunity to speak. Okay, so if we have a triangulated category, there are a number of ways to associate a space to that. So you can take the set of hearts or bounded hearts and put various metrics on it, like the tilting metric or an aisle metric. You can look at the space of slicings, or you can look at the Bridgeland stability space. And if you give yourself a bounded heart, which is a module category, then you can also think about the G-fan or the wall and chamber structure. And there are probably many other spaces by now associated with triangulated categories in various ways. So I want to talk about a relatively new beast in that zoo, which is the heart fan. And everything I talk about will be joint with my collaborators, Nathan Broomhead, David Pauksztello, and David Ploog. And I want to advocate a little bit for the heart fan on the grounds that it actually illuminates some of the connections between these other spaces associated to a triangulated category, in particular between the Bridgeland stability space and G-fans and wall and chamber structures. So that's a kind of more practical reason why you might be interested in it. Philosophically, I want to make a bold statement, and God, this is being recorded, so posterity will hear this. But the bold statement is that somehow convex geometry is the linearization of homological algebra. So the heart fan is a fundamentally convex geometric object, and I'm advocating that that's somehow the right kind of thing to look at when you linearize homological algebra like a triangulated category. Okay, so much for the kind of fluffy stuff at the beginning. The situation that I'll always be working in is thinking about a bounded heart, H, sitting inside a triangulated category, D. And the other bit of data that I want to fix from the beginning is some homomorphism from the Grothendieck group, K0 of D, equivalently K0 of H, to some finite rank abelian group. So some fixed. Usually we'll be thinking of this as finite rank and free, but it doesn't actually have to be free. It won't really matter if it has torsion, so I'm not going to fuss about that. Okay, so when we start with this data, what we can do is associate to any intermediate heart. So I have an intermediate heart with respect to H. So I'm thinking of some heart K, which is between H and its shift by 1. Then you can take that and associate what we call a heart cone to that. And that's going to be a cone CK. And it's the set of vectors in the real joule of lambda. So this is why it doesn't matter if lambda has torsion, because I'm immediately going to tensor with R to kill all the torsion anyway, and then take the joule. And it's those vectors which are positive on K. And that's shorthand for V of lambda of the class of K is greater than or equal to 0 for all K in K. Okay, so every intermediate heart gives me a heart cone, and this is a cone in this vector space, finite dimensional vector space, in the sense that it's closed under scaling by positive reals and it's closed under sums. And it is also a closed cone because it's dual. Okay, and I want to give you two perspectives on the meaning of this cone, or the meaning of vectors in this cone. the first perspective is that this heart cone, in some sense, classifies certain Serre subcategories of K. Okay, so what I mean by that is if we're given some vector v in this cone, then there is an associated kernel subcategory that I'll denote by kernel sub k of v. So this is all of the k in k, little k and big K, such that v of k is actually equal to 0. So that's, I'm thinking of that as some full subcategory of K, and it's actually a Serre subcategory. So it's closed under extensions, and it's also closed under taking subobjects and quotients. And that's easy to check. Going in the other direction, oh, and maybe I should. So any subcategory of this form, I will call a kernel subcategory. Going in the other direction, if we've got a Serre subcategory of K, then we can define a face. So I'll denote that by CK comma S. And that's defined to be the face of the heart cone where you have the vectors which evaluate to 0 on everything in S. So that's obviously a subset of CK, but it's also a face. So here, face is taken in a more general sense than you usually have for polyhedral cones. So I should have said CK needn't necessarily be polyhedral. This cone can be pretty wild. So if you've got some infinite rank Grothendieck group, and then you map vectors to your finite rank lattice in an appropriate way, you can make round cones and all kinds of things here. So we need the more general definition of face, and that says that if sum of two vectors in the cone is in that subset, then both of those vectors are in that subset. And that's an example of what I mean by convex geometry being an appropriate linearization of homological algebra. So face is basically the convex geometric linearization of Serre subcategory. Here we're just talking about sums of things in cones, and here we're talking about short exact sequences. Okay, so we have these, every vector gives you a Serre subcategory, every Serre subcategory gives you a face. It's easy to check that some vector is in the face corresponding to a Serre subcategory precisely when that Serre subcategory is contained in the kernel subcategory of V. So basically there's an adjunction between Serre subcategories and faces of this cone, and those both partial orders. So every adjunction between partial orders also gives you a bijection, and so we get a bijection between faces of this form and kernel subcategories. Okay, so that's one way of thinking about what this heart cone is doing. And there is, I should probably mention this, and I probably shouldn't because I've forgotten the right name, but you can think about a much more general thing. So you can think about the Grothendieck monoid, and there's a cone in that, and faces of that actually correspond precisely to all Serre subcategories. So this is a sort of shadow of some more general result, but the price you pay for the generality is you have to work with monoids. So life is much harder. Okay, yeah, and sorry, I cannot remember the right person to to quote for that result.
Saito?
Thank you, Path, Saito.
Yeah.
The second way that we can think about this cone is that it parameterizes lax stability functions. on functions on this hard K. So in order to understand the way in which it does this, I need a little bit more notation. So if I am given a vector v in ck, then I can talk about the tangent cone to the heart cone at that vector. And by definition, that is just the cone of the corresponding kernel subcategory. So we look at all the vectors which are positive on everything in this kernel subcategory. That also gives us a cone. And I'll draw some little pictures in a minute which justify why this deserves the name of the tangent cone at that point. But there'll be something funny that happens for certain cones, and maybe I'll say something about that. Okay, now if I take some vector in the tangent cone at v to ck, then I can look at the charge or the stability function, which is given by minus w plus iv. And the point is, this is actually a stability function, or at least a lax stability function on k. And by that, I just mean that this maps all the elements of k into the strict half space or possibly to the origin in C. So it's like they're either in the strict upper half plane, the strictly negative real axis, or possibly at the origin. And so the lax here means that we're allowed to map things to the origin. They don't have to map into here or into the strict negative axis. Okay, so I'll return to the relationship between these heart cones and lax stability functions or stability functions at the end when I talk about phase diagrams. But for now, there's just this idea that if you're given a tangent vector to a heart cone, you can write down a stability function. Okay, let me give a couple of really basic examples. So if my heart H is K is just modules for the A2 quiver, then I'm going to take lambda just to be the Grothendieck group, which is isomorphic to Z squared in this case. And that has a basis given by the classes of the two simple objects. So in lambda r star, we have a basis dual to that. So this is the first simple object and the second one. And then the heart cone is just given by the span of those. So it's all that stuff. And in terms of faces, so this is CK. The kernel subcategory here is just 0. So oops, that's also CK0. There's a face here that's given by the Serre subcategory generated by this symbol, which is the one annihilated along here. So I'll lazily just call that S2. It's really the Serre subcategory generated by that symbol. There's another face here, that's CK_S1. And there's the face at the origin, which is CKK. So for a simple length category like this, faces exactly correspond to the Serre subcategories. These are all the 4 Serre subcategories you have. How about this tangent cone construction? Well, the tangent cone here, the kernel subcategory is 0, so we're allowed any vector which is positive on 0. That's all of them. So the tangent cone is the whole R2 for a point in the interior. If we're on this face, the kernel subcategory is that generated by S2, so we have to be positive on S2. So you get this half space as the tangent cone, which is a reasonable geometric notion of tangent cone there. Similarly here, positive on S1, so you get this. And then at the origin, you have to be positive on the whole of K. So you just get back the Hart cone itself as your tangent cone. So there, everything works very nicely. Things look a little bit more peculiar if you don't take a module Hart or a length Hart, at least like this. So suppose I take coherent sheaves on P1. So now the classes I'm going to take as my basis for the Grothendieck group are the class of the structure sheaf and the class of some skyscraper. Find a color. Come here. So now the Hart cone, we're looking at vectors which have to be positive on all the line bundles and on the skyscrapers. And because I can twist the line bundles in either direction, the only vectors which are positive on everything are actually these ones. Okay, so that's the Hart cone in this case, just that single ray. And it has a non-zero kernel subcategory, so it's, oops, I just need to move this out of the way. So it's all the torsion sheaves on P1 that you get as the kernel subcategory, because this is the ray that annihilates all the skyscrapers. Okay, and also if we're looking now for the tangent cone, things look a little bit weird. So the tangent cone is all stuff which is positive on these skyscrapers. So again, it's actually a half space. So it doesn't really look like a tangent cone to this cone. And here's the point where I mutter some things about everything works much more nicely if you actually work in the Grothendieck group with the effective cones, so the cones generated by the classes of objects. And there, the dual, so we're in the dual picture, and the dual tangent cone really does look like a tangent cone to this effective cone. So the only issue with working on the Grothendieck group side is that later on, when I want to define a fan, what you would get would be a cofan, and that's a much less familiar object, and it's much harder to draw because you have lots of overlapping cones rather than things nicely lining up. But somehow the proper version of the story I'm telling you really happens on that dual side in the Grothendieck group, and it's really a story about Hart cofans. But I don't want to spend half this talk introducing a bunch of new ideas in convex geometry. I want to talk about the relationship with homological algebra, so I'm working on this dual side, and some things don't look as nice as they should. Right, I've got that off my chest, and I won't say anything about that afterwards. What I will say is that these examples are somehow typical. This is a completely typical picture for what happens with a length category with finitely many simples. And this is a completely typical picture for what happens if you take coherent sheaves on a smooth complex projective variety. So the Hart cone in the latter instance is always just a single ray like this. And the kernel subcategory is always just the torsion stuff. Okay, so I want to go back to these kernel subcategories and illustrate another relationship between what's going on with these Hart cones and the homological algebra. So if I have a kernel subcategory S in K, and then I have another intermediate Hart K prime and another kernel subcategory, and it's very important that these are kernel subcategories, not just any old set subcategories, then I can ask, when are the corresponding faces of the two Hart cones the same? And there's a very nice answer, and it's when the thick subcategories generated by these two kernel subcategories agree. And in addition, so the kernel subcategories are Serre subcategories, so I can quotient and get a new abelian category, K mod S. this is actually a bounded heart inside the quotient of D by this common thick subcategory. So I can compare it to this bounded heart, and they have to be the same. Okay, so a purely homological criterion for when two faces of two heart cones coincide. And in fact, in this case, you can really identify this face itself as a heart cone, and it's the heart cone for this bounded heart, just with respect to an appropriate quotient lattice. So all of these faces which are appearing are really in their own right heart cones for quotient categories. Okay. So that's, I think, set up enough notation for the main theorem about these things. So I now want to think about not just one cone, but all of the heart cones for all intermediate hearts and all their faces. So the heart fan is defined to be, take all these intermediate bounded hearts, take their heart cones, and then take all faces of those, and take the union of those. So this is some potentially very large set of cones inside under R star. And the point is, this is a fan. So it's a set of cones closed undertaking faces. Well, that's automatic because I've defined it that way. But the key point is that any two cones in here intersect in a common face. That's what it means to be a fan. It's also, the notation is not lax. This is actually independent of D. So you can embed this abelian category H as a bounded heart in any triangulated category you like, and construct this thing, and you'll get the same answer. So it really does depend only on the abelian category H.
Can I ask a question?
Yeah.
In this proposition, in the proposition that you said just now, right before this theorem, you made a comment that you need kernel subcategories and not just Serre subcategories.
Yeah.
But I mean, if there were just Serre subcategories, would CKS be well defined? I mean, don't you need kernel subcategories in the definition itself?
No, so this makes sense for any Serre subcategory. So here you just take the vectors in the heart cone of K, which vanish on that Serre subcategory.
Right. So is there therefore a more subtle reason as to why Serre subcategories wouldn't be enough for this proposition?
It's really because you have an adjunction between all Serre subcategories and all faces. But in order to relate them, you need to pass to the associated bijection. So you get a bijection between the kernel subcategories and the faces of the form CKS. And then, because you have a bijection, you can reasonably hope to relate what's happening with those faces and what's happening with the corresponding kernel subcategories.
Thank you.
I mean, the simple example here shows what would go wrong. So this heart cone here, this is CK0 and CK tor P1. But 0 and the skyscrapers do not generate the same thick subcategory. You really have to work with this guy, the biggest Serre subcategory.
Yeah, thank you. Yeah.
Corresponding to the face. Yeah, please do just jump in and ask me questions. Right, where was I? Yeah, this is a fan. It's independent of D. So when you have a fan, you can think about its support. So that's just the union of all the cones in the fan. So this is now just a subset of the vector space rather than a set of cones in the vector space. And there's a well-defined map that I'll call capital theta, from there to thick subcategories, so just the set of thick subcategories of D, that takes a vector in the support to the thick subcategory generated by the kernel subcategory of V. And here you can choose any Hart cone that, so any CK that contains V. There may be many. It could be in lots and lots of different cones, but the point about the proposition above is that it doesn't matter which one you choose. This is well defined. So this is a well-defined map. So it's basically saying that the cones in this Hart fan are labeled by thick subcategories. So this is also constant on relative interiors of cones. But yeah, to gloss that, you have a fan, the cones are labeled by thick subcategories. Second part says what happens if your Hart is a bit nicer. So H is length, then the Hart fan is complete. So this support is actually the whole vector space. And third thing says if it's even nicer, so H is length and has finitely many simples. And we choose the obvious lambda. So the obvious lambda here is just the Grothendieck group of H, which is finite rank free in this case. Then in this situation, we can say exactly when this Hart fan is finite, i.e. it's just a finite set of cones. And it's finite if and only if, so the following, H is tilting finite, so there are actually only finitely many tilts. And that's the same as saying that every tilt is length. Actually, it's part C of this theorem, and since he's here, I'll name check part of this that we messed up in the first version of the paper, and I think we've now got it right. But this looks like the easiest part of the theorem, but actually it's in some sense the most subtle. Okay, I'm certainly not going to give a proof, but what's the key idea? So the key idea is that you have to relate vectors in this lambda r star to tilts of H, and it's somehow well known what the relationship is. So if you give me V in lambda r star, then I can attempt at least to define a torsion pair in H. So it's a kind of proto-torsion pair whose torsion part is all those H in H, such that V of all quotients is positive. So you can look at any quotient of H inside your category, and V should be positive on that. The torsion-free part should be defined in a similar way, but looking at sub-objects, and you want that V is negative, strictly negative, for all non-zero sub-objects. No, not in Q, in H. So this thing is trying to be a torsion pair. So it's easy to check that the torsion-free part is in the right orthogonal to the torsion part. And it's also easy to check that the vector v you started with will be in the heart cone of the tilt at this when it is a torsion pair. So the tilt is FV shifted by 1 star t, and that happens when it's actually a torsion pair. So when TV and FV actually generate H in the appropriate way. Okay, and this always happens when H is length. But if you have a more complicated abelian category, these may not give you a torsion pair. That's why you only get completeness of the heart fan when H is length. Right, what else do I want to say? Anything else about this result? Right, so the point about the independence of D is that this cone, this is just minus the cone on FV intersect the cone on TV. So although the tilt itself, so this heart depends on the ambient triangulated category, and in an important way, the heart cone of it only depends on FV and TV, and they only depend on H. So that's why it doesn't matter what your ambient triangulated category is. It only depends on this torsion pair. So that gives you the independence of D. Okay. The second thing I want to say is something about how this relates to the G-fan. So this is in a more special situation. So if we take a finite dimensional algebra A, and the lambda we're interested in here is just the Grothendieck group of finite dimensional A modules, then you can also define a G-fan. I'll say roughly what this is in a second. And this is just all of the full dimensional, so the top dimensional cones and their faces inside the heart fan of the category of A modules. So the G-fan, in this situation, the G-fan is sitting inside the heart fan, and in some sense, the heart fan is a completion of the G-fan. So delta A mod, this is a completion of the G-fan. And the idea here is basically the Koenig-Yang correspondence. So what do I need to say? So the G-fan is living basically in the real version of the split Grothendieck group of the finite dimensional projectives. And that's by projective simple duality, that's K0 A mod dual. So this is where the heart fan lives as well. So it makes sense to compare them. And then by definition, full dimensional cones.
Hi, can you please say what this split Grothendieck group is?
So it's because we're working with projectives, so short exact sequences are split. So
Oh, just that. Okay.
yeah, so we're doing the same thing that you do for the Grothendieck group. It's just in this context. I mean, we have an exact category, and we're looking at split things.
Mm-hmm. Thank
you. So full dimensional cones in this G-fan basically by definition correspond to two-term silting complexes. By the Koenig-Yang correspondence, those correspond to intermediate hearts which are length. and then intermediate hearts, which are length. So these always correspond to full dimensional, indeed simplicial cones in the heart fan. So yeah, it's essentially just Koenig-Yang correspondence tells you that this is sitting inside here. Okay, definitely time to give some examples. So here's some I prepared earlier. Actually, that David Ploog prepared earlier. He did all the work of typesetting these. So here we have the heart fan of A2 mod. So as in the example I had before, where's my colors? This is the heart cone of A2 mod itself. This is the heart cone of its full shift, which is just minus that. That's obviously always the case. And then there are 3 strictly intermediate hearts. So if I tilt, in some sense, the wrong simple, then I get a semi-simple heart, whose heart cone is down here. And if I tilt the other simple, then I get hearts which are equivalent to A2 mod. And there are 2 of them kind of cycling around the single triangle, essentially, in dB of H. And those give you those 2 heart cones there. So this is a case where you have a length category, it's tilting finite, and you get a finite heart fan. So somehow the simplest situation. It's also complete because we start with something length. Here's perhaps a more interesting example. So this is nilpotent reps of the quiver with 2 vertices and an arrow in each direction. So this is a model for a rank 2 tube. So here, this is length with 2 simple objects. So the heart fan is complete, but this is not a module category. There are no projectives here. So there is no G fan, but the heart fan still exists. And there are, this is tilting finite. There are exactly these 6 tilts. And this is what the heart fan looks like. Okay. So going up from the A2 quiver, you can think about the Kronecker quiver. And now you have this countable family of tilts all giving you essentially the same heart, equivalent hearts, and their heart fans live here. And then in the limit along this ray, this is the heart cone of the coherent sheaves on P1, which occur as a tilt of this. And in fact, there are uncountably many hearts whose heart cones are given by this ray, because once you reach coherent sheaves, you can start to tilt skyscrapers one by one. So you can tilt at any subset of skyscrapers you like, and it's not going to change the heart cone. So things here are more complicated. The G fan is everything except this ray. And then in the heart fan, this ray gets added in. So that's the sense in which this is a completion. If you go to the 3 Kronecker, it's a very similar picture, but now there's a whole sector which does not correspond to length intermediate hearts. And in this sector, every single ray of rational and irrational slope, they're all in the heart fan. So the heart fan is complete because we start with the length category. So every single ray in here has to be in the heart fan. If you go to 4 Kronecker, then it's a similar picture. It's just somehow the angle of this sector increases and so on. Okay, this is another nilpotent reps example. And this is an interesting example because here you can take nilpotent reps for this quiver with 2 vertices, an arrow in one direction and 1 loop. You can tilt at one of the simple objects to get another length heart. But then if you tilt again one of the simple objects in this, you get a heart which is not length anymore. So its heart cone is no longer a simplicial cone. It's actually just a ray, and its heart cone is sitting as a face of the heart cone of K. So this is the kind of example that shows you that these statements about finiteness are a little bit subtle, because you can have the heart cone of one intermediate heart sitting as a face of the heart cone of another. So it's a little bit hard to detect that just by counting numbers of heart cones. So yeah, that's an interesting example. But again, this is still complete. We're still talking about length hearts here. So everything has been complete so far. And now if you go to coherent sheaves on P1, then if you remember, this was the heart cone for coherent sheaves along here. And then you get tilts of it, which are actually Kronecker hearts. That's this countable family here. And you just get a half plane. So here the support of the fan is this upper half plane, and you get nothing in the lower plane. And then if you go to an elliptic curve, you get a really wild fan. So this is literally every single ray in the upper half plane, rational and irrational slopes. So it's nothing like a sort of polyhedral fan, the kind of thing you consider in toric geometry. It's a pretty wild thing. Okay, so those were some basic examples. If you want nice higher dimensional examples, so I'm very 2D. If you want nice higher dimensional examples, you should ask Pausz. He's very good at those. Okay, so now I want to talk about phase diagrams and the sense in which this heart fan is a universal phase diagram. So this is somehow how it connects to Bridgeland stability. So suppose we take a stability function. So it's just a linear map from lambda to C. Mapping every object of your heart H into now really this strict half plane, so either the strict upper half plane or the strictly negative real axis. So then we can define semi-stable objects. So the semi-stable objects of phase phi are those H in H, such that the phase of any subobject is less than or equal to the phase of H, which is equal to phi. So here by phase, in the usual way, I'm just taking the argument divided by pi. So something has phase phi if its the stability function maps it onto this ray here. So that's the semi-stable objects of phase phi. And I'm going to say that Z has the Harder-Narasimhan property if each object in my abelian category H has an HN filtration. So a Harder-Narasimhan filtration, i.e. one of the form 0 into some H1 into some HN, which is H. And being a Harder-Narasimhan filtration just means that the factors, so HI over HI minus 1, have to be semi-stable of some phases phi I, which are strictly decreasing. So phi 1 strictly bigger than, all the way down to phi n. Okay, so this is the basic data for a Bridgeland stability condition would be a heart plus a stability function with the HN property and also with the support property, which I'm not going to talk about because it doesn't feature here. And the theorem is that if I take one of these things, so let's suppose that Z is a stability function with the HM property. Then what I can do is I can pull back this heart fan along the dual of Z. So the dual of Z is mapping the real vector space dual C star. So this is not C minus the origin, it's the real vector space dual of C. And that is being mapped to lambda R star. So this is the vector space where this fan delta H lives. I can pull back along this. So I just pull back each cone. That gives me a cone in here. And I will get a fan. So I get a fan which we could denote like this, which is now just a fan in C star. And the point is, this is essentially the phase diagram of this stability function. So what I mean by that is, here's a picture of C star. I'm going to choose a kind of rotated basis. So the imaginary part of your complex number is the first basis vector, and minus the real part is the second one. And we're interested in the part of the fan that lives in then this upper half plane together with the strictly negative real axis. So what we'll see here is basically a bunch of cones. So it's just a 2D fan. So we'll see some rays. And this part of the pullback is the phase diagram of Z. So what I mean by that is not only do I have these rays, but remember we had a labeling by thick subcategories. So each cone, and in particular each ray, is labeled by a thick subcategory, and those are essentially giving you the semi-stable objects. So the semi-stable objects of phase phi are given by taking the thick subcategory associated to this pullback thing, so Z star e to the pi I phi, and then just intersecting that with your heart H. So maybe this is a bit easier to understand in the examples, exactly what's going on. So coming back to these, and trying to find a color. So being a stability function, that actually means that Z star is mapping the imaginary part into the heart cone. So Z star of this basis vector imaginary part is somewhere inside the heart cone. And then if I look at the ray through that, and Z star of minus the real part has to be some tangent vector here. So if I choose that tangent vector, then I'm focusing on this half plane here. And what I'm seeing in this half plane is the phase diagram for a stability condition on H, or a stability function on H, which has this was the second simple as its lowest phase semi-stable object. Then the extension is also semi-stable, and then the second simple, the first simple is the highest phase semi-stable object. Okay, if I chose a different stability function, so corresponding to choosing this basis vector here, then I would see this half of the heart fan as my phase diagram. And now this is a stability condition in which the extension is no longer stable. So I phase ordered the simples the other way, and the extension is not semi-stable anymore. Okay. So the point is, any phase diagram for any stability condition on H is appearing inside some 2D slice in the heart fan. And you can read off the semi-stable objects by using this labeling by fixed subcategories. Being incompetent with technology. So for length hearts, then obviously you can basically choose any stability function and it will always give you a stability condition. So you will always have the HN property. And that somehow corresponds to the fact that for a length heart, the heart fan is complete. But if you go to something like the coherent sheaves on the projective line, then here we're very restricted in which stability functions you can choose, because you have to map the imaginary part into the heart cone. So here you're forced to choose some stability function that maps the imaginary part into here, and you're forced to choose a tangent vector there, which is that side, and so that you see this upper half. And this is actually essentially the only phase diagram that you can get for a stability condition with hard coherent sheaves on P1. Likewise for coherent sheaves on the elliptic curve. So the somehow bundle up in these completeness properties or failure to be complete properties of the heart fan are all of these facts, well-known facts about stability conditions. Okay, so I think maybe I have just a couple more minutes. So
like 8.
Okay, 8. I'm probably not going to use 8, but I just want to maybe say some things about generalizations of this. So far, everything has been fix a heart, you get a fan, and you can look at stability functions on that heart. But it's also possible to look at a multi-fan, so some more complicated object associated just to the triangulated category and not to any given choice of heart. So very roughly here, what you want to do is take all the heart fans for all hearts and stick them together. So you're taking a co-limit of these things over all bounded hearts inside D. So in order to do this, you don't want to think of these as fans, because fans live in the vector space, and then if I start to glue stuff together, I will get some awful overlap and I won't get anything interesting. So what you need to do is think of these as fans living over the vector space, so with a map to the vector space. So basically, when you unwind that, you're thinking of these as pre-sheaves on the post set of cones. In this vector space. So you can interpret a fan as a pre-sheaf with some extra property on this post set of cones, and then you can glue them all together as pre-sheaves. So that's a co-complete category, so there's no problem taking this co-limit, and the thing you get here is no longer a fan, but it's something called a multi-fan. So some big convex geometric object is just associated now to the triangulated category. And you can also play this game of looking at tangent spaces. So you can define tangent spaces at points of this, and you can define some kind of tangent multi-fan. And then you can look at realizing that as a space. And so this is a space which is very roughly, as you can interpret, as the space of lax stability functions on D. So points of this correspond to a choice of heart, and a stability function on D, which is allowed to be lax, so it can map non-zero objects to 0. And so sitting inside that is actually the Bridgeland stability space. So stab lambda D naturally embeds inside that. But this thing is a lot bigger. So there are stability functions in here which don't have the HN property and which don't have support. It's not something like a partial compactification. It's way bigger than that. But it does, you could, for instance, take the closure of this inside here, and that would give you a partial compactification of the Bridgeland stability space. So I guess the bonus for this is that it's quite elementary to define if you are happy just to take a big co-limit of these things, at least. It somehow just involves elementary convex geometry in the Grothendieck group. So that makes it, I think, quite an attractive thing to think about. Okay, that's all I want to say.
Thank you, Jon. Can we all unmute ourselves and give Jon a round of applause? If you have any questions for the speaker, you can ask them now. Are these co-limits computable? I mean, it looks very abstract. That's why I'm asking.
Yeah, it's very abstract. So I think, I mean, the fact that the stability space sits inside there tells you that this will be hard to compute, right? I mean, it's very hard to compute stability spaces. So in order to concretely compute this, you would have to know about every bounded heart. That's a tricky thing unless you're in a rather simple category. So it's more it's a useful theoretical construction rather than something that you're going to be easily able to actually compute.
And this is not stab alg. This is all of stab.
All of stab.
Wow. Okay, then it's really very big.
Yeah, because I mean every point in here gives you a bounded heart and a function with the H property and support. Each of those things definitely gives you a point in here.
Is there an algebraic version of this where I would go stab alg lambda D to, I don't know, but the co-limit would be taken over algebraic?
So you could look at just the full dimensional cones, the simplicial cones in here. So that is a kind of strong version of stab alg where you're actually insisting that the heart is length with finitely many simples. So usually with stab alg you also allow kind of rotations of those. So that the rotations is not quite so clear. I mean, probably you could understand what that meant, but I'm not sure it would look very nice in here. A more reasonable thing would be you could, I mean, look at the GFAN part. So just full dimensional cones in here. But I think the position I'm taking is that it's better not just to think about those, but to think about all of these cones. Even though the behavior can be quite wild, it's nicer to have something which is complete.
Right. Thank you. Any more questions or comments? I mean, I brought up stab alg just like that because when you gave us a snippet of this paper in Cambridge, we were in the context of discussing stab alg, so I was expecting.
Right. Yeah. No, that's a slightly different track. I think this doesn't sit quite so well with stab alg.
Can you also please email me the notes?
Yeah, sure. Yeah, no problem.
If we don't have any more questions for Jon, let's thank him again. There's something in the chat. Oh, thank you.
Okay.
Yeah, thank you all for coming. Next week we will have Kabir Manali Rahul as a speaker, and the week after that we will have Alex Perry, and that will be it for this year.